Welcome to QLab. In today's video we're going to be exploring the different products from electrolysis at the anode and cathode when we use different salts. Now this isn't a good one to copy at home because it's quite dangerous, and one of the products is going to be chlorine gas. So only repeat this if you really know what you're doing and you have a very well ventilated space. Now, with that, the warning all sorted, let's get started. Right, so in this video we're going to be making use of this electrolytic cell again because it allows us to collect any gases that come off the electrodes. And then we've got 3 different salts. We've got Epsom salts here, which is magnesium sulfate. So we'd expect that would give us a magnesium 2+ and a sulfate 2- ion in solution. Ordinary sea salt, you see at the back there, so that's just sodium chloride, so sodium plus, chloride minus. And then over here, got some copper sulfate in that bag at the back, which will give us copper 2+ and a sulfate 2- ion. So let's begin by first having a look at the magnesium sulfate solution. So here we have our magnesium sulfate solution. And I'm just going to prepare the test tubes that are going to go in. Ooh. There we go. There's one that I need to turn. There's another. So I'm just going to grab one, put my finger over the end, turn it around and perk it in, trying not to release or let in much air. There we have our 2 test tubes set up to collect anything that might form. But I now need to connect the wires. So let me just take these gloves off. Like before, I want the negative to be the short terminal and the positive the long. So if I, from there to the end here, then we go from the negative all the way round, connect it here. You can probably see that straight away, but I'm going to zoom in so you can see it even clearer. There's a huge amount of bubbling happening on both the anode, so this is the positive anode, and the negative cathode. And they're both bubbling a huge amount. And what's interesting is at the anode here, the pencil itself is actually being damaged. The graphite, and so it's reacting with whatever is coming off that part. Now I can tell you for a fact it's actually oxygen. Right, so if you look carefully you can see we've almost got a full tube of gas from the cathode. Now we can test what that gas is in a similar way how we did previously. So what I'm going to do is I'm going to disconnect the circuit. Ooh, there we go. You can see instantly the bubbling has stopped. I'm going to lift this tube out, but first I'm going to light a match. I'm going to hold the match just about here. And don't forget if we're going to do this test, we need to have our lab specs on. Because if it's hydrogen gas, well, we know what we're going to get. There we go. There. Little pop. So we know that hydrogen is coming off the cathode and oxygen off the anode. So what's happening here? Well, we'll have a little look into that later. Let's have a look at another solution. Now let's have a look at our sodium chloride solution. Now I should say with this experiment, I don't want you copying this one at home, because something very dangerous happens. I'm just going to use a little bit more water to rinse this through. Something very dangerous happens in this experiment. Now I've got good ventilation in this space. I've got the windows very open and some air passing by. As before, we can see bubbling straight away. You see it bubbling exceptionally quickly off both of those terminals. We've almost got a full tube of gas of our negative cathode. Now we want to test that gas, but also you can maybe see that there's a lot of bubbling off the positive anode, but interestingly, there isn't that decay we saw, lots of the carbon coming off. So I'm going to stop the reaction now by disconnecting the circuit. There we go. Ooh. Just taking this chap off, and we'll test the gas that's on the cathode, sorry. Oh, dearie me. And I'll do it the same way I did it before. I'll try to hold it up a little bit better this time though. I let it escape. Well, that was disappointing. That should have been a nice pop from hydrogen gas. But it proves to you that science is not always perfect. A lot of experiments go wrong, and it's difficult to get these things spot on every time. Now, this other gas I want us to have a look at is in this file here. And I want us to see if we can see the colour of that gas. Now it doesn't show up very well on camera at all, but it's a very pale yellowy green. Very pale. And that's because that gas that's coming off the cathode is chlorine. Chlorine gas. Cl2. So, we've got one more solution to look at. Now the last solution we're going to be looking at is copper sulfate. And that should give us copper 2+ and sulfate minus. Now, 2 minus. Now what I need to do though, because if you remember my copper sulfate is not very good, I'm going to filter it before when adding it to the electrolytic cell. So we have a nice clear solution of copper sulfate. You can see bubbling on this side. So I can see bubbling on the positive anode, but I can't see any bubbling on the cathode. So we can see that it's bubbling really vigorously from the cathode. And we're getting that sort of black gunk we observed in the first sample with magnesium sulfate. But over here, at the negative cathode, can't see any gas being evolved at all. So I wonder, and let's just have a little look at each individual electrode. You can see it from here. Look at that, look how orange that end is. That's copper metal. Copper metal that's been deposited on the positive, on the negative cathode. So instead of having hydrogen gas given off, we've got copper metal there. And in fact, you can also see here how worn away that electrode is. This one's got copper deposited on it. So, why does this happen? Well, let's have a look at all our results and start to explain them. So let's have a look at our results. Well, firstly, what were the solutions we were looking at? The first had magnesium sulfate dissolved into it, so we would expect to have a magnesium 2+ cation and a sulfate 2- anion. The second had sodium chloride, so we'd expect to have a sodium plus cation and a chloride minus anion. And the third was copper sulfate, so we'd expect to have a copper 2+ cation and a sulfate 2- anion. But don't forget we're in water, so we also have for all of these the potential of H+ cations and OH- anions. And so we can see that at the cathode we can potentially have a reaction with either for the first solution, magnesium 2+ or H+, the second solution with sodium plus or H+, and the third solution with copper 2+ or H+. And the same can be done for the anode. We have multiple anions and multiple cations. So which ones react? Well, let's have a look at the product from the first reaction. We had hydrogen gas. So the hydrogen gas must have come from the H+ cation. So we know that when we have magnesium sulfate in solution, well, the H+ reacts preferentially to the magnesium 2+. What did we see for the second one? Oh, there we go. So the H2 comes from the H+. When the second one, we saw the same. Hydrogen gas. And that came from the H+. So it reacted preferentially to sodium in solution. And what about the last one? This was the really interesting one, wasn't it? It was copper solid. So that copper solid must have come from the copper 2+ cations reacting. So, how do we predict what happens at the cathode? Well, let's have a little look at the reaction we saw in the previous video about the cathode. So we had 2H+ plus 2 electrons going to hydrogen gas. So those H+ cations, they were gaining an electron. They were being reduced. So what we need to think about is how easy it is to reduce different things. So we need to consider how likely a cation is to accept an electron. And there's a really handy way we can look at this using the reactivity series. So can you remember with this reactivity series, as we go from gold all the way up to potassium, things are more likely to give away an electron. And you can actually think about it then the opposite way, that from potassium down to gold, they're less likely to give up an electron, or in fact more likely to grab one. So gold is really likely to hold on to an electron. And so what we see here is that if something is more likely to give away an electron, like potassium or magnesium or sodium, or even tin and iron, then in aqueous solution, the H plus is more likely to grab onto that electron that's available on the cathode. And so in aqueous solution, anything below hydrogen in the reactivity series will accept the electron, and that results in metal deposits. So remember, we saw copper. Well, you can also do it with silver and gold, and that's how you can plate things in silver and gold, electroplating. But if we have any of these metals above hydrogen, we'll just get hydrogen gas given off. So that's a nice easy one to remember. Let's have a look at the anode. So the anode product, when we had magnesium sulfate, we just had oxygen gas, didn't we? And that's very similar to the reaction we looked at in the previous video when we did the electrolysis of water. And it's the OH minus reacting to give us the oxygen gas. Now what about with sodium chloride? Well, in this case we had chlorine gas, and there's only one place those chlorine atoms can have come from, and that's those chlorine minus anions. So when we have a chloride anion, that will react preferentially. And then with the final one, well, we're back to oxygen gas. And so it's the same as with magnesium sulfate or with the water, OH minus reacting to give us oxygen gas. Now, let's have a little think about how we predict these reactions at the anode. And I'm going to show you what happens to chlorine. Because remember, it's the opposite to the cathode. So at the cathode, something gains an electron and is reduced, but at the anode, something loses an electron and is oxidized. So what we want to think about here is how easily something can lose an electron. Now, the halogens, that's fluorine, chlorine, bromine and iodine, their anions, which are fluoride, chloride, bromide and iodide, are all more likely to give away their electron, or more easily give away their electron, than the OH minus anion. And so, in aqueous solution, oxygen gas is produced at the anode unless there's one of those halides present. So if you were to have potassium iodide, or let's think of another, cesium chloride, you would have iodine or chlorine evolved at the anode. But if you don't have any of those halides, it'll always be oxygen. So let's summarise what we've just learnt. The cathode, that negative electrode that will have the positive cations come towards it, will in aqueous solution, and it's really important to remember this is aqueous solution, there's lots of water molecules around, hydrogen gas is produced unless a less reactive species on the reactivity series is present, such as copper, silver or gold. That's a really easy one to remember. And at the anode, that positive electrode, so all the negative anions go towards that, in aqueous solution, oxygen gas is produced unless a halide, such as fluoride, chloride,
bromide or iodide is present. In which case, if one of those is present, their respective elemental form will be given off. So with fluoride you'll get fluorine gas, chloride, chlorine gas. Bromide, well, you'll get bromine develop, which will vapour off and be very unpleasant. And iodide to iodine. It's important to remember that these rules are for aqueous solutions. For molten liquids, the rules are usually much simpler because you don't have many choices of anions or cations. So in molten sodium chloride, you only have sodium plus and you only have chloride minus. So the chloride minus, well, that'll go to the anode and you'll get chlorine gas, and the sodium plus, it'll go to the cathode and you'll get sodium metal. So in molten liquids, it's really simple. But in aqueous solution, you've always got to think about that H plus and the OH minus.
Well, that's the end of our short series on the basics of electrolysis. I hope you enjoyed them. If you didn't see the previous two videos, they should be appearing about here. I'll also put them in the description box. If there's anything you'd like me to investigate or some science you'd like me to look into, I'd love to hear from you. It's nice reading your comments, and I'll see you in the next video.